Hello, everyone, and welcome to today's webinar. My name is Eric Gross, and I'll be presenting today's subject. For you regular attenders, you can tell that my voice is a little bit different. This is not Paul. Paul's taking a break this month. In fact, we were just joking just a few seconds ago that we were hoping that nobody would think Paul was out sick or anything like that. Nope, he's well and he's doing good. And so we're all, he's going to be fine. Okay, well, you are in there, like Paul always says, you are in the right place if you are interested in 6 areas of consideration when starting a new PCB design. A little housekeeping before we get started. This will likely take up the entire hour, so there won't be any time for questions at the end, but please do enter any questions into the panel. We do have people from 9 Dots that are monitoring the questions, and hopefully they will give you some answers during the webinar. So the webinar topic, 6 areas of consideration when starting a new PCB design. What this webinar is, it's really a discussion about making good early decisions in a design process and not missing the critical or simple items. So you'll hear me talk a lot about early decisions or the beginning of a design, things like that. So that is the theme of this webinar. We're not necessarily going to design anything in here, but we are just talking about good decisions early on. This is also based on the first module of our PCB methodology course that is currently in development. This is going to be an excellent course, probably a 3-day course, and we are going to cover in depth all the things that we're going to talk about today. But obviously we only have an hour, so we're going to brush through. In fact, we're going to even brush through the first module, but you'll kind of get an idea of what we're doing. What this is, and this is not intended to be a webinar on how to design. And this is not a comprehensive list of items. I know there's a lot of people on this webinar that are doing different things, and the diversity of what everybody's working on. They may have 8 areas of consideration. They may have many, many more, but these are the 6 I've picked for this webinar. And just to be upfront, if you're a 20-year veteran in the PCB design, then you've probably learned most of what I'm going to mention today. And you've probably learned it the hard way, just like I did. But if you're newer into the industry, then I hope you'll stick around with us and pick up a few tips that might save you a spin of your own someday. That would be, if you can save a spin, I've done my job. So the 6 key areas we're going to talk about is fabrication, electrical, mechanical, regulatory, procurement, DFM, DFT. You can tell that in an hour, we're not going to be able to get too far in depth on all these. But if you notice this guy with the jackhammer, we came up with this. Photo because kind of, you know, if you're 99% done with a PCB and something comes up and the PCB has to be changed or ripped apart, it kind of feels like a jackhammer going into rock. So that was kind of a humorous picture that we came up with. So I do have a polling question to get started with. And what this is what I want to do is say, how much time do you typically spend on finding solutions versus considering potential consequences? So as engineers, we're not only in the business of finding solutions, but we want to know what's going to go wrong too. So if you could answer that real quick, I'd appreciate it. Okay, great. Yeah, it's pretty. The middle road is pretty even. Yeah, I was thinking either 70-30 or 60-40 in my case, and I guess it depends on what you're designing and things like that. But definitely, that makes a lot of sense. And of course, the 90% solution, 10% is way down, which that's good to know, because what we need to do is we want to think of everything. And speaking of that, the first question I have is, why didn't I think of that? How many times have I come up with, have I had to say that to myself? And why do we sometimes miss the obvious? Well, new designs can be exciting. You know, you get a new design and your boss tells you to start something, you want to get started real quick on it. You've learned a lot of things from your last design that you're going to put into this one, so you're feeling pretty good about things. You're pushing to get started and show progress. So the first thing you're doing is you're starting to, starting to fill in the schematic, and you're probably going after low-hanging fruit, some of the circuits that you know well. So you're going through that, and since you know it well, you're not kind of thinking of all the consequences and things like that. You're always feeling a bit behind in a project, even at the beginning. So you want to show progress rather than putting on the brakes for a while and figuring out, what could possibly, what could be the consequences of what I'm doing here. So we all get into that kind of trap. And of course, everything works great during the schematic entry, or does it? The schematic entry has always been my favorite part of a design, because you're designing something that you know is going to work. You kind of know it's going to work. Nobody sends out a board to the fabricator with problems that they know are there. They think the thing's going to be perfect, and so they move on. So sometimes there are things that you might not have recognized or might not have thought of, and those you find out during the testing of the prototype. The other part of this is I wish you would have told me that earlier. This is all about asking the right questions. And the reason I say that is people don't know the impacts of postponed or changed decisions. For instance, marketing, they may come to you late in the program and say, hey, you know what, we really need this thing to be about half the size that it was before, or you know, we need some other feature that would really give us a good marketing edge. Well, they need to know what those impacts are going to be. Management, you know, I was in a company one time when we were developing a video camera, and we were halfway through the thing, and our CEO walked in one day out of the blue and said, hey, let's make this thing battery powered. And so that was like a 3-month statement right there, because now all of a sudden everything that didn't matter about power was now a big deal as far as power management and low power consumption and things like that. So that can be a big thing. Some things we've never taught, you know, almost never think about is the legal side of things. Again, I had a project one time. It was a baby monitor, and near the end, and these questions will come up at the end if you don't ask the right questions. There was a material that may have been on a hazard. You know, actually, I think it was a choking hazard. The legal department looked at it and said, hey, this little gizmo you have on here could fall. If it ever falls off, you know, baby could actually swallow that. So again, going to legal first and asking about these things can save you enormous time, because again, the legal stuff may come right at the very end when you're ready to ship this product. Okay? And even mechanical and software engineers, you know, mechanical might come to you over here and say, you know, I need a 125 mil tooling hole right here, or mounting hole. Well, that's going to be a big deal. It's much better to make sure at the very beginning you've got all the mounting holes and tooling holes and all those types of things, and make sure you have, you know, agreed with your mechanical people and your software engineers on what the design is. It's always wise to ask the right questions early. So you might get a spec that says what you have to do, but always ask the right questions. Maybe somebody didn't put the right thing in the spec, or maybe somebody just isn't aware of things that could go wrong. And of course, late decisions are usually costly ones. That could probably be the word almost, or always, I should say. Not almost, always, but I don't like to use always, so I'll just say usually at this point. So let's start with fabrication assembly considerations. Kind of a weird place to start, because, you know, normally on a design we start with the schematic, right? Well, before you start with a schematic, you really want to know who your fabricator and assembler is, if you can. I know a lot of people might not be able to, but if you can know who they are, it's very important, because that's going to drive some of the parts you decide to use, some of the materials you decide to use, some of the rules you're going to use in your design rules. This all matters with the fabrication. Please don't, you know, you never want to release a PCB and send it off to a fabricator you don't know. You should have all that information very early on in the process. And make sure you know who's doing your prototype and your production. You definitely want to make sure your production assemblers and your production fabricators have the same materials as whoever does your prototype, has the same technology, has the same capabilities. Capabilities and limitations are very important. And people, if a prototype shop onshore can do it, it doesn't always mean a production shop overseas can do it. So make sure you're aware of all those things. And of course, material constraints. There are probably people on this webinar that have incredible material constraints that they have to deal with. And so that's always very important to come up very early in the design. And of course, special requirements. And I have no idea what those would be for all of you out there, but everybody's got some sort of special requirement. And so spending some time, even before you start the schematic entry, if you can think all the way through the program or the project and think of some sort of special requirements you might have, it will give you that opportunity to ask the right questions to the right people. So determine your IPC class rating. If you're doing a class 1 non-critical low power reliability products, you know, you should specify that. It's going to save you some money. A class 1 product would be like a gizmo, like a Happy Meal toy. If that thing breaks on the way, as long as it keeps lighting up until it gets home, you're probably going to be okay. Nobody's going to go back to McDonald's and return that. It's a class 1 device. Class 2 is high reliability. It's important for customer satisfaction. A cell phone, you know, 15, 20 years ago is probably not a class 2, but now it's definitely a class 2. When people are spending $1,200 on a cell phone and had everything they own on it, you better believe that customer satisfaction is important. And class 3 is major consequences for failure, like avionics, medical equipment, things like that. So this is something you specify to your fabricator, and they will adjust their inspections and their testing based on this. So you don't want to overspec anything, but you certainly don't want to underspec it either. So knowing your class rating early on in the project will drive a lot of different things, like, again, parts, rules, things like that. Special requirements, of course, harsh environments and chemical, moisture, and temperature. My first job out of college was for Hughes Space and Communications Company. We worked on geosynchronous satellites, and I learned a lot about working in vacuum, the kind of thermal problems that you have in there. Spacecraft, the side of the spacecraft that's facing the sun is blazing hot, and the side that's facing deep space is super cold, and there's all kinds of issues you got to deal with there. So if you have special harsh environments, that's a good thing to bring up early on in the design. Other special requirements, mechanical strength. If you got a very large board like this, knowing where all your mounting holes and things like that are, very, very important, especially when it comes to connectors in the middle of a board like this. If somebody's not very gentle and jams that connector in there and you don't have any kind of support here, you're going to actually bend that board and probably have many of these little components pop off the board. And if you have a BGA in there, you could have all kinds of cold solder joints and stuff like that. So, or I'm sorry, you could have all kinds of cracking and things like that. So knowing where your mounting holes, knowing your high impact environments. We had a design once where we had a large electrolytic capacitor that was surface mount, and of course, if anybody dropped the equipment, that thing just sheared right off. So we ended up having to put some epoxy on that later. The assembler had to put epoxy on it to make sure stuff like that wouldn't happen. So always think about high impact environments, and even if it's not normally high impacts, people do drop equipment sometimes, and you don't want things to just fall apart when they drop. Yeah, so make sure you don't have bend and twist in your board, things like that. Connector mating force, again, if you have a very large connector, sometimes we get so focused on using surface mount devices that if you put a large connector on a surface mount and it comes out where a customer can actually connect to it, and they've jammed the connector in real hard, or they yank on it real hard, or they trip on the wire coming out, you could yank that connector right off the board. So thinking about things like that, about mechanical strength, if it takes a through-hole connector or adding mounting brackets to it, you got to do it. And then a rigid flex design, repeated motion. Very, very different. There's a very different design methodology for rigid flex if you are just bending the flex once during an assembly. If the assembler is bending it once and it never gets bent again, that's a whole different design than something that gets bent every day or many times a day with a customer. So knowing what your repeated motion requirements are is very important. I have another polling question here. How often do you work with rigid flex designs? And kind of the reason we're asking this is we have not had a webinar on this yet, and we'd like to do that, but we want to make sure that people would be open to that first. So I thought it would be a nice little break and listening to me, and then you could maybe get some information on this. Okay, good. Okay, so not very many people regularly. So maybe we'll end up offering something like that. Maybe some people don't use it simply because they don't want to use it, or they're not too aware of how to use it, rigid flex. So maybe we'll do something like that in the future. Thank you very much for sending that out. Okay, electrical considerations. Again, we're going to go quickly through this, but I want to go through a couple things that maybe people haven't thought about before. High-speed design or not. If you're designing a flashlight with a battery, then it's a DC. Then it's not high speed. But if you're designing just about anything in the modern world, you need to at least consider high-speed elements of the design. Even at low frequencies, I know a lot of people have gone over this before, but even at low clock rates, you're still going to have some pretty sharp edge rates these days on components. That's just the way they make them now. They can make them cheaper by making them smaller. And by making them smaller, they become faster. And so you can get very fast edge rates. And if you're not treating even low data rate signals correctly, you're going to get all kinds of signal integrity issues. You're going to get EMI issues. You're getting this, all this frequency element of this thing. So always consider whether this is a high speed or design or not, and always tend toward a high speed, even if it doesn't seem like it. Impedance matching throughout the path of the signal. Sometimes we think about the output impedance of the driver, or the input impedance of the receiver, or even the stack up, having the path be matched impedance. But we have to remember that throughout the path, the signal has to be matched. So looking at the signal and reference plane is very, very important. So always keep that in mind. And know the effects of inductance and capacitance on every element of your circuit. You know, that's one thing. It's such a simple thing, inductance and capacitance, but if you don't think of it very often, you kind of start thinking about it, you know. So it's one of those things where you want to always remember that what the effects of, especially on high speed, what's going to be the effects of inductance as the frequency increases, or the effect of capacitance on your designs. We go through that. We're going to go through that a lot in our training, and so that's just one thing I just wanted to bring up, and hopefully everybody can you know, deal with that and go out and learn about that. Clocks and timing. Clocks have to have very good signal integrity. We can get away with a lot when it comes to a data line or an address line. If it has a little bit of a jitter, or it's not quite so clean, as long as we have a 1 or a 0, we're pretty good. But clocks have to have special signal integrity and treated special. Any ringing or jitter on it is going to cause timing issues, especially jitter. Ringing could cause false triggers, things like that. So clocks and timing are a very, very important part of this. Match propagation delay does not always mean match length. These days, timing is so important for some of these devices that we can't only use a lot of the EDA tools will allow us to check to see if traces are the same length. Well, that's just not good enough anymore, because we have to know if traces are run on the top and the bottom of the board versus the internal parts of the board, they are going to propagate at a different speed. So no longer can we, in some of these designs, rely on just matched lengths. We have to match the propagation. So it's super important for this. And this is thing it's in red letters because it's something that I had to learn very much the hard way. These things, and what I said is, things that aren't working always get the attention. When you get that first proto back and something's not working, it is all hands on deck, right? Everybody's looking at it, everybody's figuring it out, you get a solution, you move on. What I say here is watch out for things that are working. They could be marginal. Probably one of the hardest days in my engineering career was having to walk into my boss's office and let him know that we had to spin a board because something I missed that was fairly easy to find. It was a reset circuit, seemed to be working fine. We had actually already spun the board 2 or 3 times. Everything had always worked, and it wasn't until the very end that I figured out that not only was the timing not right, it just wasn't working right. And it's a tough thing. So you got to watch out for things that are working, because they could be marginal. And the other lesson here is that and this is not an excuse, I inherited that design, that reset circuit, from another design. And what the lesson is there is, even though you inherit a design from somebody else or inherit a circuit, it doesn't always mean it's going to work for you. So a lot of times, let's face it, we all like to grab somebody else's design for a transceiver or something like that, or a power supply, and throw it into our design. It saves us a lot of time and hassle. But just make sure that when you do that, you are actually going to look at the performance in your design. Super important. Mixed signal digital circuits can be fairly dirty and work well. Not true for analog. You've got a lot of crap on this signal, but logically it's going to work fine. You're going to get 1s here and you're going to get 0s there. No, not a big deal. You may have EMI issues and things like that, but for this discussion, that's going to work. This is not going to work at all, right? This is going to be a problem. Careful consideration early on needs to be made to keep noise out of the analog, and that's all noise. Analog circuits are very, very happy to just process any noise within their bandwidth. So if you're within the bandwidth of that analog circuit, it has no idea whether it's something signal or whether it's noise. It's gonna just be dumb and happy and keep doing what it's supposed to do, whether it's signal or noise. And don't forget about power supply noise. That's probably the biggest thing in an analog circuit, is to make sure your power supply noise is low. Make sure you're measuring it correctly. Sometimes we measure power supply noise incorrectly if we have too big of, if we have large ground loops and things like that. So measure the power supply noise and get to know how to measure power supply noise properly. Power supplies, I put this, I saw this picture of this burning power supply, and it brought back a memory of when I actually was troubleshooting a board, and I actually lit a capacitor on fire. I mean, literally, it was coming out like a candle. It was, and, of course, I got razzed pretty good for it. I think I even got a nickname for it afterwards, but I don't know, it kind of amused me when I saw these flames blowing out of there. Anyway, power distribution is as important as any electrical circuit you're going to design on a board. Sometimes, and I think some people that have been around a long time, they know that power supplies are going to be so important. But if you're new to designing boards, you may think the power supply is just kind of it's a DC power supply. What could go wrong? Let's just slap something in there and move on. Nothing could be further from the truth. Power supplies and power distribution is as important as any high-speed digital circuit, any kind of PHY circuit, any kind of analog circuit you'll have on the board. And one of the reasons why a poor performing analog or digital circuit affects its own performance, the power supply can ruin the performance of all the circuits. You can imagine getting a board back. If the power supply is bad and very, very bad, you may have to spin that board to fix the power supply, and it might have been so bad that it hid other problems on the board, right? It just swamped out other problems. So once you fix that power supply and it's working fine, now all of a sudden all these other problems start coming up because now you've fixed that. So that's another reason to get that early on, to make sure you use the right power distribution and make sure that's right, because you don't want to have to deal with there's enough problems to deal with than having a poor performing power supply, because that can just really make your life miserable. Some of the decisions are pretty obvious: voltage and current ratings, making a list of what the voltages are and what the currents you need. Linear switching, if linear supplies are very quiet, they're easy, they're cheap. But if you have a large input to output voltage variation and you need a lot of current, you're going to have to go with the switching supply, and that's going to be a whole different game, because you're going to have to worry about noise and making sure that thing is laid out correctly. So you got to make those decisions very, very early on. Isolated versus non-isolated. If you got safety issues or other reasons you have to have it isolated, it's nice to know early, because then you can kind of design your board and your chassis or your whole system based on that. Thermals, of course, are important. Thermals, most of the hotter components are in your power supply, so you want to make sure you lay those out and not put those in your sensitive components like imagers or any kind of circuit that's going to be sensitive to temperature. And of course, layout is super important. And I would say all DC-DC kind of buck and boost regulators and all these kinds of regulators will have layout recommendations. Whether they're perfect or not, you can decide later, but that's very important. Of course, decoupling. One of the things that some people don't always think about is we should never, ever, unless again you're building a flashlight with a battery, you should, or a Happy Meal tool with a battery or something, never think of a DC supply as being DC anymore. Rapidly changing currents due to digital switching or any kind of other thing on the board that will cause currents to change creates frequency. Okay, so you might think, hey, this is a 5-volt DC supply. I don't have to worry about inductance. I don't have to worry about capacitance. No, that's not true at all, because as soon as that DC supply as soon as the current begins to vary at all, if you've got a power supply on one end of the board and you've got a load on the other end, and that load demands current now because gates have closed or whatever, gates have turned on and it demands current, that power supply has to first overcome all the inductance between the output of it and the input of the supply. It has to overcome that first, because remember, an inductor, it's part of its main purpose in life really is to oppose a change in current. That's what it does. It's made to do that. And so inductance is your enemy, and of course capacitance, it's one of its main purposes in life is to oppose a change in voltage. When voltage starts to drop, it gives up some of its charge to keep that voltage up. So that's why decoupling is very important. And the other thing about decoupling, there's always an optimal decoupling, and there's papers out there everywhere. There's tools to figure it out. There's optimal decoupling, but the very nice thing about decoupling that you can decide early on is that if you have room for it, add extra decoupling, you can always take it off, okay? It doesn't hurt a design to take off a decoupling cap if you don't need it. And so after first proto, you can play around with decoupling and figure out what's best for you. And of course, that is if you have room. If you don't have room, then sorry. But that's why decoupling caps are very nice to work with. Mechanical considerations, so much, right? And this is all early on. You need to know your board outline. That might determine what parts you're going to even put on your schematic. That's why the board outline, you may not need the specific board outline, but you definitely need to have a rough idea to know how much real estate you're going to have. It could drive decisions on components. It could drive all kinds of things, interfaces, things like that. Mounting holes are super important. Make sure you get them right the first time. You don't want to have to move a mounting hole. And remember, if a mechanical engineer gives you this mounting hole, says I want a 125 mil mounting hole, you get to kind of decide what the annular ring is. But the question to ask them is, hey, is there a screw head that's going to be, how big is the screw head? How big is the standoff underneath? What kind of standoff? Is it going to be plastic? Is it going to be metal? All these things, don't just rely on a position of a mounting hole and a size. You got to think all the way around that thing and make sure you're not going to, because if all of a sudden this standoff is another 100 mils or 200 mils around here, and you've routed or placed things near there, you're going to have to be ripping things up. So these are the questions you want to ask early. Keep out areas, of course, if you're given a keep out area, you want to put that in there really early. Height requirements. There may be a bracket or something that comes around here. You got to have height requirements in there. Make sure you put those in your rules. And connector placement. This is an important one because if you work with your mechanical engineer or you are the mechanical engineer and you tell your electrical person or your designer, hey, I want these connectors. I'm going to give you the position I want your connectors to be in, right? And they are assuming at that point that your origin to this connector or your reference point is in the middle of the connector. Well, it could be that the person that built this part actually made pin 1 the origin or the reference point of that connector. So you may get through an entire board layout, you think you've done the right thing, you put it in the exact position your mechanical engineer wants it in, and you hand it over to him. When you're all done, you hand him the step file, and he or she comes back and says, hey, these connectors aren't even close, right? Now you're ripping up that board, you're getting out that jackhammer, and it's going to feel like that, right? You're going to rip everything up, and it's going to take a lot of time. So early decision, making sure everybody understands what's going on is super important. And then mechanical support, you might want to have to work with your mechanical engineer to tell he or she that, hey, we got a part over here that's very sensitive to bend and twist on the board. I need a couple of mounting holes in the corners of it or something like that. So much more to consider. Thermals, there's a lot of tools out there to look at thermals. It's a whole different, putting models into the tools. That might have to be done early. You can't do that at the very beginning, but once you place your hot components, you can actually start running thermals. Integration, trying to make sure that you don't design in something that cannot be slid into a slot or into a housing or things like that. Cable routing is super important. You can't just put a connector somewhere and just assume the cable routing is going to be okay. Cable routing, we'll talk about this in the EMC, EMI section, is that cable routing is super important inside of a chassis. You don't want to pick up extra noise on a cable and send it out of your box. And of course, something like this, if you've turned that around, you're in big trouble, right? Or if you have a connector like this and you put a large component right here and it can't get in there, that's always a big deal. And of course, grounding and chassis connections or isolation, that's something to work with your mechanicals and whether or not you want to ground to the chassis or not like that. And of course, shielding, big deal there. Not only mechanical integration, but also thermals and all kinds of things you got to deal with there. And this is the one this is the good news. The EE and ME collaboration tools are getting very, very good. You can send over in steps. It is in steps, but in steps of your board, you can just send over a step file or send over some sort of design over to your mechanical person, or if you are the mechanical person, maybe you do both. And you can load these designs into the tool, and you can actually, they're getting so good that you can actually start manipulating things in the other person's tool, and it's working out really well. And I remember early on in my career, there was not very much 3D type viewing of anything. And so you really didn't get a good look at what your board's going to look like until you got it back from the first proto. Now I can look at a board and it actually looks like a picture of a board, and it's just so fantastic. And I do stress to a lot of people during our training classes that use the 3D tools. It's not cheating at all. You know, it is so, I've found so many issues with in the 3D view that I would have never picked up anywhere else. So that's very good news about how that's all working out. So regulatory, oh, my voice will change every time I talk about regulatory considerations, because I would say regulatory considerations are the toughest part of engineering. And I could be wrong about that, because you know, I've been in a few industries now, telecom, a lot of video security type of stuff. So regulatory things can literally drive you crazy if you're not careful. And it is absolutely never too early to think about regulatory decisions. Even when you're starting your schematic, you need to know what kind of protection you're going to put on your board. You're going to need to know what kind of class rating you're going to be. It's just everything. You should know everything about regulatory, everything that you're going to have to pass regulatory wise. You should know before you start your schematic even. Know your product classification. You need to know if you're class B, class A, what kinds of things you're going to have a UL inspection on this thing. All this thing is super important, even at the level of schematic entry. Where you know your product will be sold. You know, each country, it's getting pretty even, you know, pretty widespread. Some of the, but you know, some of the European standards are not the same as the US standards. So knowing where this is going to be sold, and if it's going to be sold somewhere that has different compliance standards, you got to know about that. Like even Australia has their own compliance standards. A lot of it is common, but knowing where it's going to be sold is very important. What is required and what is expected? And I write this down because it's been hard for me at times. I said, how many times have you had to have a mark on your product just because your competitor does? It's that's something that just drives me crazy. We were told, hey, you got to be FCC Class B on this thing, which is a big deal, you know, compared to Class A. It's a 10 dB difference in emissions. And you ask, well, why? This is a consumer product. Why do you need that? And your marketing department might say, and for good reason, hey, because our competitor has Class B on theirs. And so next thing you know, you are trying to meet Class B classification just because your competitor does. So it's the way it is. You know, we want to sell product, and if that's the way you have to sell product, then we have to do it. I do have another polling question I want to bring up. It has to do with, so I was lucky in one of my companies, we actually had compliance engineers and safety engineers. So I'm wondering, do you have access to compliance and or safety engineers? And of course, one of the things is no, I'm on my own, or I am a compliance safety engineer. So if you could answer that real quick, it'd be very interesting for me to know. Okay, that's kind of what I expect. I'm glad to see that I think it says 26% have their own engineering staff. And some people are using consultants. Now, so I would suggest, this is a big suggestion here, is that the problem spots are really obvious and usually difficult to find in regulatory situations. You know, like I said, I worked for a company that had a compliance department and safety engineers, and it was just the best thing that I could ever want in a company, because they were super valuable to helping us with this. Now, you know, we are at 9 Dots, we do a lot of electrical design and things like that, and we don't have that. We don't have a compliance or safety engineer on staff, but a lot of us have been through it a lot. But I'll just tell you, you know, even last week I was working on design, and I had a question regarding a UL problem, and that, you know, that question could have taken me all day to find, even if I could have even found it. But what I did instead is I have a UL person that I go to, and I paid him a few dollars to answer my questions. And I can tell you right now, if you have the opportunity to even, you know, just hire a consultant or things like that, it's so well worth it if you're not sure about your regulatory or your design and how it's going to pass. Because remember, regulatory issues always come up at the end of the program. Usually, you built a board, you've got it working. One of the last things we do is try and get through regulatory or compliance, and it fails, and now you could spend weeks or even months working on that. Whereas hiring a consultant or something like that can save you enormous time and money. Always think of cables as common mode noise, and as a broadcast media, I say this out of experience. You can design a board as quiet as possible with all the right ways of doing it. And as soon as you slap a cable on that thing and it comes out of a chassis or something like that, if you have cables that haven't been routed correctly, or you have common mode noise on your power supplies or your ground planes, that stuff is the worst to have to worry about, and it comes out hard and fast. And that it creates the cable that you've connected on there becomes an antenna, and it's just a nightmare. So always, every time you have a cable, a product with a cable that hangs off of it, always remember that you're gonna have to deal with that kind of thing. And try not to pull your hair out. I had kind of a reputation in our compliance lab as being kind of out of control, because I never got mad at people, but boy, did I get mad at things that were going wrong. And so that guy up there, he's a lot better looking than me, but that's basically what I was like in the compliance lab. And we get together every once in a while and joke about it every once in a while too. But yeah, I was not easy to work with in the compliance lab. So let's go on to procurement considerations. Seems like a benign subject, but really, really not. Define critical, optional, and combined components very, very early, especially the critical ones. I usually come up with a spreadsheet and I say, there may be 5 or 6 components that are absolutely critical. There's not any way I'm going to design in a certain FPGA or a certain processor or a certain Ethernet PHY, and it's locked in. So critical components, those are the ones we got to have. Optional would be something like a RS422 transceiver, or maybe some of the memory devices that you can get multiple sources on, things like that. And then commodity components would be all the other stuff that is very common out there. The trap here, though, is if you design in a part that can't be used, you can make a great design unbuildable. And what I was going to mention about the commodity components is that it always surprises me when I hear that we have a worldwide capacitor shortage. And you're like, that can't be right, right? Well, yeah, it can be right. You never know what happens in different countries. Many years ago, we had the tsunamis that went through Japan and took out a lot of production houses for parts like that. You just never know what's going to happen. And of course, when Apple comes out with a new cell phone or something like that, there's going to be a shortage of just about everything. So even commodity components can be iffy at times. So we want to look at lead times, end of life issues, allocation, and import-export issues is something I never really thought about before until it got too late. And that is that if you have a part that cannot for some reason be imported into a country, think about the impacts there. You have literally already gone into production. You've built maybe thousands or tens of thousands of these things. They're in boxes, they're on shipping crates, they're on boats. They get to another country and you find out that they will not go through customs because you have some sort of part or material on that board that cannot be sold in that country. That is a huge, huge problem that, basically, you were done. It was over and now it's not. So be careful of that. So design for manufacturing and design for test considerations. So this could obviously be, this could be a whole subject of its own and probably be a whole day of our training. So we're gonna blast through this pretty darn fast. So what I recommend, in addition to publications, fabricators and assemblers provide a lot of information and guidelines to what their capabilities are. I just did a quick thing on the web yesterday. Eurocircuits is a great company that a lot of people use. They've got these PCB design guidelines that you can just go through and get all their guidelines that they have. And a lot of these companies are doing the same things. And so, but if you know who your fabricator is and your assembler is, going through their PCB design guidelines is very important to do very, very early on. Again, even before you start the schematic if possible, because it might drive certain decisions in your design. Minor variations in the design can sometimes produce higher yields, but of course, on the flip side, minor deviations from supplier recommendations can have the exact opposite effect. You know, if you put a 6 mil, you can't tell from this, but this is a 6 mil hole here, and you find out, in fact, I just found out the other day, well, it's pretty common actually, but I was told the other day that an 8 mil hole will not drive your costs up at all anymore. A 6 mil hole, they're going to be breaking a lot of bits when they're doing a 6 mil hole in a 62 mil board. And you know, you might have just put in a 6 mil hole, even though you have this giant annular ring around here, you might have put in a 6 mil hole just because that's what the person before me did, right? Well, that's going to cost you. And certain fabricators may not come back and say, hey, you know, they don't want to question your design. So they're going to use that 6 mil bit because you hadn't looked at what their standard is. All you had to do is change that to an 8 mil hole and you save yourself some money. Same thing as this, you can't tell over here, but this is a 2 mil trace and a 2 mil space. If it didn't have to be like that, if it has to be like that, then you know that it is. But if it doesn't have to be like that, then you don't want to design in something that doesn't need to be there, or it's going to drive costs. And capabilities are changing all the time, so take advantage of the improvements and new techniques. This is another example of inheriting a previous design. A previous design might have been 5 years old or even older. You inherit that design, you kind of keep the same rules, you keep everything the same. Well, these fabricators and assemblers are getting better and better every day. You know, gosh, if you look back, it's funny. I was actually on a conference call yesterday with a fabricator, and this is a good lesson. Having a contact at a fabricator or an assembler is just so important to be able to talk to them. We had a little meeting with about 6 of us, and as we were all introducing ourselves, the person at the fabricator said, yeah, I've been in this business since 1982. And I kind of chimed in and I said, so have there been any big changes since 1982? And everybody had a nice chuckle, you know. And so he, you know, we were kind of BSing a little bit, and he talked about some of the things that were changing. But he sat there and taught us. I was ready to send this board out to them, and there were a few things on that board that even after all these years, he was explaining some things. And it was specifically about solder mask defined parts, and he went into an explanation that was so fantastic that everybody was just mesmerized by what he knew and how he knew it. And he really did save us a big deal of time, and just being able to talk to him on the phone rather than getting emails or looking at some of the stuff. And of course, they are keeping track of the very, very latest advancements in assembly. So having somebody that you can call up on the phone or talk to is just so important and saves you lots of time. And remember, fabricators and assemblers, they want you to be just as successful as you want to be, right? If you're successful, they're going to be successful. You're going to order more boards, they're going to build more boards, everybody's going to win. So nobody wants to do something that's not practical. So use that resource when you can. Some of the DFM considerations, panel optimization. You know, you come over here and remember, a lot of us don't do panelization. We let the fabricators do that, but it's nice to know what the size is. If somebody builds this board just slightly bigger, you know, for no real reason, they could have made it a little bit smaller. You might only get a 4x4 out of this panel instead of a 5x5. If you would have built it just slightly smaller, you're going to get a lot more parts. And if this is a very high quantity product that you're doing, you're going to save a ton of money just by making a very small amount of adjustment. Materials, you got to make sure that the materials are available and they're not going to have to go out and order. Sometimes we add tolerances, or we create our own stack up here, and we might spec in something that's not a standard thickness of a prepreg, for instance. Your fabricator might take that and go, oh, you know, we don't have that, but we can order it. It's going to take us 6 or 8 weeks. But if you go to this other prepreg, we can do it tomorrow if you want. So using a lot of these EDA tools now will have these stack up managers, and they work well for everything, but there's nothing like going to your fabricator and saying, hey, is this going to work? How can I make it better? How can I set the cores and the prepregs the way you like it? And when you start talking about micro vias and buried vias and blind vias, you have to be extremely careful how you set up this stack up. And you know what? Why add that, to your list of things to do when fabricators are very, very happy to do it for you? They don't want to have complicated designs that they're going to have low yields on or have materials that they can't come up with. They want to help you. So don't forget to use those. Drill sizes and annular rings. You have to come up with these decisions when you go in the layout. How big do I want this annular ring? I can make it real big, and any kind of drill wander is going to be good, but I'm not going to get as many routing lanes through here. Or I can make it very small, and I'm going to get some of this stuff here. If I'm in a Class 2 device, that's okay. I don't like it, but it can pass. But if I have a Class 3 device and I do something like this, I'm asking for really low yields. So these kinds of decisions need to be made before you start laying out the board, because it's easy to make this smaller, but it is never easy to make this bigger, right? So those are the kinds of things you want to know early on in the design. And of course, reduction of number of different parts is pretty obvious. It keeps people from having to keep a lot of different parts on inventory. When they install it, when they actually load the machine, pick and place machines, they can have less reels in there and things like that. And of course, reduction of handle assembly. If you had to look at this every morning, this thing of boards, and you were going to do this all day long, you can bet that the beginning of the day, this solder job's going to be a little bit better than the end of the day. So hand assembly, you want to avoid as much as possible, not only for the cost, but definitely for reliability as well. And good documentation is important. Fabricators and assemblers, if you don't tell them what to do, they'll do whatever their standard is, okay? Which probably is okay 90% of the time, but not 100% of the time. You could definitely get a board back that you did not intend to have happen, or something that you didn't intend to happen only because you didn't tell them the way you wanted to do it. We have a PCB foundations course that we do at 9.Connects, and we talk a lot about documentation and a lot about the process of building a PCB. So this methodology class will be more of how to design the PCB, whereas our foundations course is a fantastic course on learning the process of a PCB. And we talk a lot about documentation, and it'll save you lots of time and money if you do good documentation. So DFT, this is actually, so we're gonna go through this really quick. Paul Taubman, that usually does this webinar, you normally hear his voice if you're a regular attender. He used to be a test engineer, and when he lights up when you talk about testing, because he's been through it all, the good and the bad, and the ugly, I guess. So design for tests can save enormous amounts of time in the long run. And it's something that a lot of people don't think about at the very beginning of a design, right? The last thing we want to, when we're put down that first part on our schematic, we're not really thinking about testing that board yet. So starting at the very beginning is very important. And nobody likes to add test points late in the layout. It's always a bad thing. Adding test capability for both development and production is important. If you've got test points where you can test, we talked about power supply measurements earlier. You can put test points down to measure power supplies. Very good thing to do. And of course, into production, you want to have test points and connectors for programming and things like that. And know what type of testing will be done in production, and make sure it's not being limited due to interference access issues. So if you have a flying probe test that you're going to do, make sure you understand how flying probe works, that you're not going to put components in the way of other components, or put a component underneath, or a test point underneath like a shelf of a connector or things like that. You can probably tell I'm rushing a little bit right now. That is my last slide. So luckily I didn't want to run over it all. And Paul Taubman, he's going to jump on for a second and give you a little bit of information. And I think we have one more polling question as well. Thank you very much for attending, and let Paul's going to be coming on now.
All right, very good. If you want, go ahead and answer that question that we just posted here. And in the meantime, Eric, just to let you know that we've been monitoring the questions. You don't have anything immediately that needs your answering, but if you do have any questions for Eric, please do write those down in the questions panel. He'll take a look at those while I speak about 9.Connects for a few moments. But we'll also finish up this poll over here. Great stuff. Well, there you go, Eric. Nice job for your first effort on webinars here. So thank you very much, everybody, for attending. I'm glad that you're able to get a lot of good stuff out of that here today. In the meantime, I'm going to switch over my screen so that you guys can see what I'm doing here. I'd like to talk a few moments about 9.connects, in particular about this PCB methodology class that Eric has been alluding to. So you are here for a reason. That number one, there's a lot of decisions to be made when starting a PCB, and probably so many of them, and you may have done them so many times that you tend to forget that there are actually a lot of decisions that need to be made here, and ones that we tend to forget have a lot of consequences. And a lot of these decisions are definitely like pouring concrete, and it's a monumental effort to undo or to change them. And Eric was not kidding. We really spent a lot of time trying to find a picture that was most apropos for how we feel that what happens when you've gone down a certain path and you realize you got to tear up this whole thing and take it back several steps. It's just not a pleasant experience. And of course, decisions do have consequences, because if you never really thought about it, a lot of times that layout, if you're a layout person or a layout person, is really a diplomat of sorts. They really have got to get information from a lot of different areas just beyond electrical. Obviously you got to talk with the mechanical, but you also have to talk with those people who are in fabrication. You got to talk with the program managers. You may even have to be interfacing with marketing, possibly even with customers as well. So you're getting a lot of inputs from a lot of areas, and decisions that you make as a layout person can have an impact on somebody and you wouldn't even necessarily know it. So they do have consequences though, and it's really amazing if you think about it. One of the things we always throw out, especially in our other class, PCB Foundations, is that there's really no field of electrical engineering that doesn't require a printed circuit board in the long run. You may not be directly involved with it, but at some point, even if it's fiber optics or RF, it's gonna make its way to a printed circuit board. So something to consider. So the webinar you saw today is definitely an outline, and you may say, well, an outline of what? Well, it's an outline of this class we were trying to put together that we've seen, based on some of the things we've talked about with our customers, the need for knowledge beyond a tool. It's great to learn a tool. We're more than happy to teach you things like Altium Designer, but a lot of times there's knowledge that has to be known above and beyond the tool, because the tool is only as good as the person making use of the tool itself. And also a method to proceed for each new design. It's always been interesting to me, and I've seen this, and Eric has probably seen this as well, especially in smaller companies where you have to do your own thing. You're taking it from cradle to grave. And as a result, there's never necessarily a common process. And you can see those individuals who have a good process and those who don't, and maybe it's not because they're not bad layout folks, it's just because they want to get to the fun stuff, which is the layout, as opposed to doing a lot of the setup before then. So having a method to proceed with new design. And of course, the understanding the impacts of the decisions that I just mentioned a moment ago in the last slide. So with that being said, with this PCB methodology class that we are forming and putting together, and it's coming together slowly but steadily, is to be a process class and not a tool class. So process classes are a lot more difficult to put together than a tool class. They're easy to do, but unfortunately, they're easy to do, but the exercises get a little more difficult or a little more involved. And so we have to do a little bit more thinking when we do these type of classes. Secondly, we do want it to be hands-on, but at the same time, we're looking at it as like a double diamond slope, that we would kind of expect those people to already know how to run the tool. So it's not just a matter of running the tool. The exercises would take you, for example, if we were to give in something a little bit deeper into stack ups, we would already expect the individual to know where the stack up tool was, and maybe have already played with it. But now we'd go deeper into, okay, how would we want to set up a particular stack up for a 6-layer board or for an 8-layer board? And of course, we want to go beyond the layout. So as I mentioned before, the idea would be is that the rules as they relate to assembly, for example, or stack ups as they relate to fabrication, or placement as it relates to mechanical, or even routing as it relates to compliance and regulations. So we want to take it beyond just, okay, we're going to lay out this board to get it to manufacturing. What happens when we do certain things, and how do they impact other aspects of the entire design process? So that is what we're trying to develop over here. You've gotten to see a preview of the overall layout of what we're going to probably talk about within this type of class. And so I just say stay tuned, because hopefully by year's end, we'll be able to make a formal announcement as to what this class specifically is and when we'll be able to hold it. But until then, if you have more, if you want more information about who we are, what we do, services that we provide, please do check us out at 9.connects.com. And so with that, Eric, did you have any things that you wanted to jump in and ask or say at this point?
No, thanks for doing that, and I really appreciate everybody's time, and I'm really excited about developing this course, and I can't wait to start teaching it too. And I think everybody in our organization is going to be kind of contributing to it. I mean, everybody in our organization has 20 plus years of experience, and it's going to be a fantastic class. Thank you.
With that, I don't see any questions that we haven't already been able to answer offline here, so we will end it here at the hour. Thank you very much for joining us here today, and we look forward to having you at our next webinar.